the instruction 1 to 6 actually from a shell code. So to detect this, we try to assign corresponding suspicious value to each instructions right before return instructions. So if it is far away from return instructions, the value get to be low. And if it's close, the value is high. So since we have the complete transport, we could count the accumulated suspicious values. So if the communicated suspicious values exceed a predefined number, we know that it could be a return-oriented attack. We could also use branch tracing support to detect return to libc attacks. So we first do some static analysis trying to extract the code graph of program. And then we check the control flow graph during the runtime. For example, if we have some illegal control transfers from address 3 to exec, we know that this is actually not in the original control flow graph of the program. So we can see that address 3 is not in the legal set, which could call execve. So we know that this is an attack. There are also some cases that using some indirect calling of some sensitive system calls like exvc. For example, the address 2 that got exploited and it called execve, and in this case we could trace it back to some neighbors, and if we found some anomalies in this chain, we could see that there are some possible attacks. So this is summarize the PMU features we used to detect all these attacks. So we branch trace stores to detect all these attacks, and we also could use some branch misprediction to catch code injection attacks, IPLB misses to catch product injection attacks. So we have already have some preliminary results of our work. So we evaluate our systems with 2 real-world applications with real vulnerabilities. So we use Samba, which contains a vulnerability, and SQID, which is a proxy. So we attack this vulnerability using all these 3 means, and we successfully detect all these attacks. We also show that our tools can be used to do some post-attack diagnosis. So we could record the samples at the time of attacking. So we could trace back from the shell code back to the one which called this shell code and back. Then we could see how this vulnerability got exploited. We also do some measurement on the performance, and we use a bunch of applications, and this graph depicts the performance overhead. So for some applications like Apache, we got a very low performance overhead, and the maximum overhead is get tau, which is CPU intensive. We also compare the performance overhead of a pure performance counters and the overhead with our systems, and we can see that our systems actually cause very little performance degradation. So to conclude, in this talk, we made a cube observation that performance deviations in performance counters is actually significant between attack run and normal run. So we could use performance counters to accurately capture the performance the security attacks and do some diagnosis. But in our future, we are trying to lower our overhead and do some compiler operations to reduce overhead. Thank you. and I'd like to take questions.
How can you explain in more detail about how you decide whether an event is a breach or not? And breach? Is it really a security breach?
Okay, security breach. Yeah.
So how do you decide that? And is there a false positive in your method?
Yeah, a very good question. So we use some heuristic algorithms to do some detection, like oriented program. We just count the association values. So it may have some positive, false positives, and false negatives. And also we rely on some static analysis. We need to analyze the boundaries to get the control flow graph. So in C programs it's not easy to get an accurate one. So we also may have some false positives and false negatives. But we didn't experience that in our evaluation.
Other question?
I noticed you use BTS to store the return address. But my question is, if the return address is dynamic, how did you judge this code belongs to malware or others?
So your question is, since there's some return addresses are actually dynamic, so how could our systems got the samples for this? So since performance counters is a CPU feature, and it's dynamic in nature, so it basically captures what the program is killed. So if the return address is dynamic, the PMU can basically record the addresses and the control transports.
Last question.
This is really cool. Do you think that it might be possible to also use this for detecting exploits inside the Linux kernel?
I think so, but it may require more engineering work. Linux kernel is quite complex, and currently we rely on some kind of features like the pub events support to do this. And if we apply this to Linux kernel, I think maybe we need to need someone sitting behind the Linux. So we couldn't. We will make sure that our tools won't be compromised.
Actually, we have time for one more. Is there any more questions?
I think you use PEBS, but as I know, PEBS is based on sampling. It doesn't guarantee that you capture every event occurring in the system. And many attacks just occur once. Like if I just jump to the malicious code, then I not get the privilege. So how can you handle this?
Okay, it's a very good question. So we actually use PEBS plus BTS. So BTS is itself thorough in nature, because it can capture all control flow transports inside the program. So it's not sampling based for BTS. So there's no program that we need not to worry about missing some events. But if for ground trace store, if I use the ITOB miss, there may be some problems. Yeah, thank you.
Okay, thank you.